No, I think the presenter, it's
Do you have?
no, I don't have. You should bring it. All right, so thank you all for coming today, as if you have a choice. So today we're doing a rehearsal for Maria, and well, there are quite a few undergrad interns, which I hope it will help you to get some idea of what research life is. And for those who's well, not yet, but well, more or less, whose defense should be coming, you can still also get some idea. So Maria will, wow, she's been here since I joined. She joined this university, and she's almost finishing her degree. So this is probably her last seminar as a student. Yes, part-time student, I hope. And so I'm gonna time her today, and if you have you guys actually some suggestions for her, just please go ahead and give her some hints. So okay, Maria, I'm gonna time you, and you can.
Yeah, meanwhile, I just want to say thank you. You know, it's early and cold, but you're here, so thank you so much. And please give me comments, because it's a draft and first rehearsal. Like anything you spot out, please let me know so I can improve before my defense date. So yeah, and welcome for you all for my topic, which is automation of ultrasound assessment of scoliosis with robotic scanning. And this is the interdisciplinary research between biomedical engineering department and mechanical engineering department. So the scoliosis, what is it? Actually, it's a spinal deformity more than 10 degrees. And the risk groups is adolescents, so 11 to 18 years, and predominantly girls. It's actually much more frequent. So, and in adolescents, like literature, we see that there is 2 to 3% of the frequencies appearances of the scoliosis in adolescents, and of course, with the age, as age increases, the percentage in the population also increases. And we don't know the cause of the adolescent scoliosis. That's the problem to treat it. Thus, we have to actually see if there is any progression occurs during the rapid growth of these adolescents, and take actions such as bracing, surgery if the progression becomes too big. So the common gold standard method for assessment of scoliosis is X-ray, which is actually hazard, has X-ray radiation, and it was shown that the frequent X-ray exposure actually increases the breast cancer. So the method for scoliosis assessment with ultrasound was invented as a radiation-free method, actually within PolyU. And this method allows to reconstruct the spinal curve. So you can see on the screen, as operator moves the probe through the spine and collects the images and spatial data to reconstruct the spinal curve. So what we can observe that the operator has to apply the force, has to move upwards, and has to follow the spinal curve. This is a non-trivial task for a non-experienced operator. So here comes the research question. So we just saw that the human can perform this kind of scanning, and there are, of course, some limitations of this approach. The human inconsistency in force application, and also the requirements for the training of the operator. There are also research showing that the 90% of the sonographers, they experience the musculoskeletal disorders, so they experience pain during the frequent scanning. And of course, now it's very hot topic is a close contact with a human. Now we have to try to avoid it. So the question is, can ultrasound plus robotic perform as good as human operator? So if it can, the advantages would be high precision and repeatability, and the comparable cost starting from take A, this is the cost of the robotic arm, and reduce the repetitive motion and human contacts. So far, the literature review of the spinal applications focuses on lumbar spine and mostly on guided interventions in lumbar regions, such as facet joint injection and epidural injection for anesthesia. So we are one of the pioneers of working on the scoliosis with the robotic arm. And here is the first publication which came on this topic from our lab. So then if you want to focus on the robotic and the scoliosis, how do we track the curvature of the spine? There are several methods. For example, we can use the prior information such as pre-operative images like MRI and CT to pre-plan the path for the navigation. So the limitations of such approach could be that, well, the pre-operative images are quite hard to get. You need to collaborate with the hospitals, and not every lab can do so. So the manual path planning is actually also the other main issue. So it must be done by a doctor and who can interpret images well and pass this plan. And then it requires multiple transformation because it also includes the camera internal as external sensor. So the other approach is actually very related to the scoliosis. And this approach uses the camera to detect the spinal curvature on the phantoms. So the work represents 30 different curvatures on one phantom. So this is a flexible phantom, which can change the curvature. And using the camera, they detect and pre-plan before the actual procedure, the curve, the path. So the limitation is, yeah, we need an external sensor and again, the multiple transformations. And it's not stable if the subject moves. Let's say we pre-plan first the trajectory and then subject moves. And then they didn't do any test on the scoliosis subject, so we don't know exactly how it performs. And the scanning was done in different positions from the clinical relevant position, so in the prone. And so the third method to plan and well to navigate the spine, it's actually using the reinforcement learning. So basically, this reinforcement learning technology is about finding the correct location by itself by doing many trials in virtual environment and learning how to achieve the goal in optimal way. So these two works present the sacrum detection. So let's say the robot starts from the random position and it's then incrementally moves like 5 millimeters and 5 degrees rotation in any direction. And then it learns what is the optimal combination of those moves to get to the sacrum point. Then the other work did also for the spinal applications. But as you can see here, actually, so this work is, even though it's very good in terms of no need of external sensor and autonomous behavior, but it's actually mainly focuses on reaching the goal rather than how good the trajectory is meanwhile, which is for us quite important to follow the spinal curvature. So here we also need manually select goal, and test was done only on offline subjects, so basically on the reconstructed volumes. And the data set, I would say, rather small in terms of the images. So the first initiative to actually follow the spine is to find the center of the spine in each given frame, which would be a Spinous process. So the Spinous process methods, the detection of Spinous process are starting from face symmetry, which is quite old methods to detect bone surfaces, to the segmentation methods, which is quite consuming in terms of the manpower, in terms of labeling them. So then what would be the solution from us, the proposed solution? So first is the application, for the scoliosis with robotic in clinically relevant position, so similar to X-ray and EOS standard. Then instead of using the phase symmetry, which is not accurate, and manual segmentation, which requires manpower, a lot of manpower, we use the deep learning process, deep localization. I will explain later how. And instead of using external sensor, we're using the ultrasound itself. So instead of predefined path, it's also quite flexible to use the real-time path and detect the Spinous process on continuous image streams instead of, as previous method, used just to detect the Spinous process only on the frame when it's present. We also can deal with inconsistency of the Spinous process in the stream of the images. And then test on scoliosis subjects, and has a much larger data set than the previous works. So what is the contributional novelty? Let's put it like this. This is the first study that proposes an automatic spinal curve navigation system using real-time ultrasound images. And this is the first study to address a reliability of scoliosis robotic ultrasound assessment with comparison to manual ultrasound assessment. So this is the proposed robotic scoliosis assessment approach. So as you can see here, the robot moves upwards, and at the same time, it relies on the ultrasound images to detect the Spinous process and correct the path in the horizontal direction. Then it also applies the constant force and rotation in terms of being about the normal vector to subject skin. So yeah, you can see the procedure. Then we move further, and I will explain a little bit about the control. So the constant force is reached according to PID control, and 10-15 newtons were selected from the previous work for the spinal robotic application. So in terms of BMI, it can be selected from this range. The PID control relies on the error of the force sensor, from the force sensor. So from the set point, which we want, this 10 or 15 newtons, and the measurements, actual measurements coming from the force sensor. So the rotation is also force-based, and it uses the momentum, also coming from the measurements of the force sensor. So the ultrasound-based control is actually a variation of proportional control, but with extra exponential smoothing to, let's say, cut off all the rapid movements which may occur due to the predictions, although the prediction is quite accurate. So the learning-based approach for the Spinous process detection is actually, you can see this network is based on the ResNet. It has backbone as a convolutional layers, and it also has two heads. So one head is actually predicts the location of the Spinous process, and it has a deconvolutional layers to generate the heat map. This heat map actually shows where, like in this heat map, each pixel is representing the probability of being Spinous process or non-Spinous process. And as you can see, like the Gaussian distribution in the like the black image and white spot, this is the location of the Spinous process. So the second head is actually the region detection head. So it can classify each image as belonging to sacrum level, lumbar level, and thoracic level in the spine. I will explain later why we need it. And this network gave us quite good results on the test set of the subjects, 5 subjects, 95 for the classification and 97 for the localization task. Here, how we deal with the inconsistency of the predictions, because as we know in the spine, we have alternating the Spinous process and gap, Spinous process and gap. in between those spinuses. So how do we deal with those moments when we have no prediction, or the prediction is like less than 50% confidence, right? So we have to deal somehow with that. And for this, actually, we're using the continuous Kalman path, which is based on the Kalman filter. And this actually helps us to make it much smoother. And on the 5 test subjects, we had just 3.3 millimeter or average distance error. So as you remember, I showed you before the network with 2 heads. So the second head is actually used for prediction of the region, classification of the region of the spine. And this is used for adjusting the rotation of the probe, because it was observed that in the lumbar curve usually is slightly less curvy than the thoracic one. Thus, when the thoracic region is predicted, when it started, so it's switching from the lumbar coefficient to the thoracic coefficient, and a rotation becomes bigger. This was shown to help in the scanning, and as you can see, the results improved in the thoracic region. So this is the output of the network. So as you can see, it's clearly differentiates from the lumbar region to the thoracic region and the sacrum. So the results of the robotic scanning were as follows. Here I would show you what to pay attention for. So this is the manual scanning, this is the robotic scanning. So the robotic scanning is clearly maintaining the Spinous process more in the center of the field of view of the probe. And this is the manual scanning. So it has more inconsistency in the behavior. And here, this one example is for the moderate scoliosis, so the larger curve. And this one we can see also quite a smoother following than the manual one. Then we went for the comparison study of the robotic and manual to test reliability and some user cases. So for this comparison study, we had 23 subjects, adolescents, and we scanned them 3 times with manual approach and 3 times with robotic approach. And those result in 6 scans. 2 raters were measuring the deformity on those scans. So I will explain later. So this is the setup. I think some of you saw it in GH, and this setup is actually exactly as it looks like. So the only thing you should know is that like an extra thing. So this scan is actually taking 60 seconds, and the robotic scan takes 2 minutes, so twice longer. This is done to assure that the number of the ultrasound frames were similar in both cases, so the reconstruction would be more fair to compare. Why we're gonna do the same speed? Because the hardware limitations of the robotic combination of all the systems were outputting us less frequency frame rate than the, this built-in already custom, company-made solution. Then we go to the deformity angle measurements principles. So, okay, we collected those 6 scans, and now we have to measure the curvature to actually compare the curvatures between robotic and manual scan. How do we measure them? So there's a standard approach. This one, it's called the Cobb angle scoliosis, which is used in radiography. And this is based on the finding the apex of the curve, and then finding the most tilted vertebra from above apex and below. So this one is the similar approach, which is done by the manual labeling in the software, and then automatically calculating from that software the angles. So it's this similar approach, finding the most tilted vertebrae. So for the two raters, I mentioned for the two raters, one rater was less experienced than the other. So one was a newcomer, just received the basic training, and the other had 5 years of experience of the measuring the curves. So those are the scanning results. You just can try to pause here a bit and see. So in the left side is the robotic one, then the right side is the manual one for the 6 different people. In general, you can try to make your own outcomes from those images, but I would say that the borders of the images looks quite smoother for the robotic one, and the lumbar region is more prominent for the robotic one than for the manual one. So the reliability results shows us that the highest reliability results were obtained for the inter-rater reliability with the robotic method for the rater 2, the experienced rater. And well, the less reliable, let's say, it's the manual for the rater 1. So for the inter-rater reliability was quite good, both the methods, and for the correlation results, we can see that the correlation, like the robotic 2 manual angles for rater 2 and rater 1 has quite a similar correlation coefficient. So we also performed the survey in this study, asking the subjects how comfortable you are during the robotic and manual scanning. And there were no significant difference between the results. So for the robotic was 7.8 out of 10, and for the manual 8.7. Yeah, of course, manual, I think still more worked through, so it's performing a bit better. And some of the issues we noticed during the scanning. So in some cases for the manual scanning, for the 4 subjects, we found out that there were some missing spots in the images, which may be due to the inconsistent contact with the skin. Which were perfectly fine with the robotic one. And for quite many subjects, we observed that for the manual scanning, the lumbar region was less prominent. So I would say it's due to the force control again, because the robotic in the lumbar region, and lumbar region is let's say it has more layers of the fat here. So in general, a bit more of the force needed to get the good image. And for the third case we observed is this one is the robotic one, and this one is the manual one. So as you can see here, the curve is not perfectly centered, but more than that, we lose some features from the back, from the sides, which might be good for the other methods of the curve estimation. So for the robotic scanning, of course, also were some issues. And one of the issues we observed is that even though we did this special rotation in the thoracic region, some of the cases, like 2 in our case, had a narrow space in between of the bones, so the probe could not go through. This is the tight scapular bones, which is known. And for human operator, usually they can rotate it and go. But for the robotic approach, so far there is no method in this study to predict these kind of subjects. And one subject had quite irregularity in this region. So it has a quite steep concavity in this side. So it has to be somehow applied more gel or so, but this is how it comes from the first scanning. So it also, there's so far no ways to solve this unless we observe the subject before. And the third case is actually the side effect of the force application. As we saw in the previous slides, the force control is actually helping us to see the more features, and it's good to maintain the contact. But here is the downside of this force control, because some subjects, they feel maybe they have a weaker musculoskeletal system and they bend it. But it was just observed for the 3 subjects, but they were bending when they were in contact with the robots. Thus, the curvature appeared to be much higher. So coming back to the question, can the robots scan the human back as good as the experienced operator? We just showed in this study that this system is actually doing pretty good in terms of has a novel spinal curvature navigation methods and rotation adjustment method, which gives us reliable, based on the human study and reliability test, curvatures. We presented the benefits of employing the robotic methods, and it requires no external sensors such as camera, which makes the multiplication of the transparencies much easier and cheaper approach. So, of course, the limitations are there, and experiments so far were focusing only on mild scoliosis, there were no X-ray images for curve angle reference, which would be quite relevant. And the comparison was done for an experienced operator. And what if the robotic method outperforms a non-experienced operator? That could be the next question. So the conclusions that we did a robotic system for scoliosis assessment with smart curvature following and the reliability of methods were tested, and the study paves the way for further research into the robotic approach on a larger group of participants with different severity of the scoliosis, and well, eventually, hopefully, commercialization. So I thank you all of my teams. I'm lucky to have 2. And I want to find one more picture with maybe even broader group, but somehow lost. But I will work on that before the defense. And yeah, here the publications arises from the work. And we even got the final list of Best Poster Paper Award in the Macau AROS conference. And thank you so much for the listening, and I hope you have some questions. Oh, good. Then I can speak slower. Yeah. Yeah. Or maybe we just keep it, so I know the questions. Yeah, I think so too. Yeah. questions. Okay. Yeah. Yeah. Thank you. Yeah, but I decided not to. Yeah. Okay. Yeah. Yeah. Okay. Yeah. Then I can get some more results. Okay. Yeah. Yeah. Mm. Mm. Yeah. Okay. So also about people from mechanical engineering, like since it's not your area, please tell me like what was not clear so I can maybe make it more clear. Yeah, true. Mhm. Mm, mhm. Yeah. Yeah, you mean to show the limitations of the approach, right? Yes. Yeah. Okay. I show. I think I did. So maybe you mean something else. Like those the limitations of the work and also limitations and this one and this one. So is it okay like this? Yeah. So how about the referencing? Like this one is because I used two different styles, so I'm not sure which one is better. Like this one to show for the work or like here. Mm. Mm. Any suggestions? Okay. Mm. I think both of them robotic. Both of them robotics. Yeah. Yeah, seems so. Yeah, medical robotics.
ultrasound? What is the advantage of ultrasound? Just the radiation of traditional.
Mm.
That example, scanning images.
All right. How about the related work section? Do you think it's sufficient to cover the navigation, robotic navigation approaches like those?
Okay, so why mention that he's a bit concerned about the validity of ultrasound. This here mentioned that X-ray call is actually the traditional method, but there's no validation in this study. No fundamental measure.
Okay. So you mean to show first that the ultrasound is valid? You mean this one? Yeah. Okay, so I have to mention that it was validated. Okay. Yeah. Any other comments, unclear things, spots you noticed? Yeah.
Just to make sure,
Hmm. Yeah. Mm. Yeah, so this one. Yeah, so I send the velocity commands in. So actually here I initiate the another frame. So it's called init at the time of the start of the robotic procedure, and then I basically take this as a reference frame. Yeah. So I like transform it back, but all the all the velocities are done in TCP space. So it's like if you see Z is facing towards the subject here, like along the normal vector, so then it goes along Z. So it's velocities in TCP space. Yeah, so then it transforms, sure, yeah, back. Mm. Okay, yeah, all right, then thank you. Yeah, Happy New Year.